Uh, this was where we left. So in the previous hour, we talked about ResNet, and we then talked about GoogleNet. And you can see both of them in the comparison table here. And this is AlexNet, this is VGG, this is GoogleNet, and this is the first ResNet. And there are a lot of ResNet versions. And as you can see, ResNet is scalable. For that matter, it's much valuable than GoogleNet as an architecture. However, both of these studies had their own contribution. Just like I said, ResNet had this residual connection idea, which gave us the infinite capability to make networks deeper and deeper. And GoogleNet was studying an idea to make the blocks wider so that we could handle multi-scale information, so that it would give the network the inherent ability to process multi-scale data. Okay. One of them is 2014, one of them is 2015, and these two ideas have their own contribution. And when both papers were published, people started to use these ideas, and frankly, the owner of these papers decided to use each other's ideas as well. So I'll first talk about the Inception Resonance, then I'm going to talk about the ResNet with Inception layer as well. So this was Inception Resonance, the Inception guys, this guy Sizagedi, Google, who did the original Inception, decided to add a residual block to their network. And what they thought was, okay, we had this block, which is capable of multi-scale information, but we don't have residual networks. That's why we cannot get deeper. Let's use this Inception Resonance. They adopted residual connections to their architecture. So the idea was introduce residual connections that add the output of the convolution operation of the Inception module to the input. So let me show it on the figure, if you can see it on your screens. It's here. So this is one of the later versions of the Inception module. This is Inception module version 3 or 4, I guess. And these are the more earlier versions. So as you can see, without this connection, yeah, this Inception module, one going to 1 by 1, then another 1 by 1 to be shaped for 3 by 3, 1 by 1, 3 by 3. If you have other connections, and you can change the Inception module you use here. There are different versions of the Inception module. But in the end, the idea was, in addition to the output of it, we add the input actuation as well. So if I just call this guy X, this function F, I'm talking about this function F of X, here I have X plus F of X, the original ResNet idea, nothing else. And it was pretty much better compared to Inception module, actually. Some implementation details. The original paper didn't use batch norm after summation to train the model on a single GPU to fit the entire model on a single GPU. So what I'm trying to say is they needed batch norm because they needed to shape the activations so that they don't lose the gradients. But with residual connections, they had a lesser need for gradients in the also. And the GPUs they used those days were, much weaker compared to the GPUs we can use today. It was found out that Inception Resident models were able to achieve higher accuracies with lower epochs, and they could be trained much easily, much faster. And this is how it looks, guys. This is how it looks. So this is the Inception Resident. Inception residual block, Inception residual block, Inception residual block, and in the end you have this. So let's see where it stands. Inception Resident, can you find it? I'm trying to find it, but I cannot find it. Inception Resonance version 2 here. They have different versions, but the idea is the same. You have an Inception module with residual connections, and you create a network out of it. Well, pretty good, huh? Pretty good. Because this is ResNet 100 something. It is better than that. So the idea was to make it better than ResNet and InceptionNet. So they are here. Sorry, I'm sorry, just remind. The thing is, guys, I'm telling to Zoom people, what I'm showing you on Zoom screen is not projected to the screen because we have a problem with the projection. That's why I'm using another computer to project it to the screen projector. And sometimes they are not synchronized. They have to just warm me up. I'm sorry, just always warm me. Just let me show you this so that you understand if I'm in the wrong place. Okay, so just if they do not match, tell me. Okay, so Inception Resident is here. So much better than ResNets, better than Google Nets. I don't have to tell you this. Okay, Inception Resident here. Yes, yes, because it's another computer. Okay, Inception Resident. So apparently, since combination of the two ideas, using the inception model with the residual connection, worked better than even the ResNet, because ResNet is fantastic. They had their own contributions, I would say. And it's still one of the best classification networks you can find. It's not cheap, but it's very good. Okay. And the ResNet guys also did it. The ResNet guys said, so this is Kai Ming-hye. And by that time, Kai Ming-hye moved to Facebook AI from Microsoft China. Okay, we are the founders of Residual Nets. And these guys, Google guys, have some sort of wider blocks idea. Can we apply it to residual networks? And parallel to what Google people did in Inception Resident, they had the residual network with exception connections. They called inceptions, and there are different versions, inception, exceptions. I don't get into the details of it. They call it the ResNext, like the next residual network version in 2017. And they proposed the concept of cardinality, an additional dimension to depth and width of a CNN. It was making the convolution layers wider, actually, nothing else. And shows that aggregating residual blocks with the same topology and hyperparameters is more effective in gaining accuracy, going deeper and wider. So this was the idea. This was their network. Still, what you can see is there's an input, there is a residual connection. There are, you see, a total 32 paths here. I'm not showing it to you guys. Please warn me. 32 paths here. There are 32 paths here. And what they do is, first by one blocks, they change the depth. Then using different convolutional blocks, which the idea of cardinality here, they propose, they create some features, and they feed it, they concatenate it, they sum it up. They sum it up, guys. This is a different idea. They don't concatenate, they sum it up. So different features are combined, and then they add the residual connection as well. So ResNet is also very good. It's a bit more efficient compared to Inception ResNet. And if you see the big picture, it is somewhere around here. So ResNext. So saying ResNext. It's more efficient. It requires less number of operations. So this is Inception version 3. This is ResNet. This is Inception This is ResNext. This is Inception ResNet version 2. So it was a constant battle between these ideas, and these go, and I'm not going to talk about them, but we have this neural architecture search nets, which is an idea where you create a network to look for the best network, and they had this NASnet. But again, I mean, the study on classification networks architecture is still going on. Neural architecture search is a way of not doing it in a handcrafted manner. However, at this level, I mean, at this introductory level deep learning course, what we are trying to do is, we are trying to get the ability to design these networks in a handcrafted manner. Although the features we find are not handcrafted, the networks we design are handcrafted. And we are trying to understand these design patterns. Why should we use a residual connection? Why should we use a one-by-one convolutional block? When do we need multi-scale information? And if we need multi-scale information, how can we make the convolutional blocks wider? What size of filters to use? This is a hyperparameter that we must optimize. So how to optimize it? So analyzing these networks, ResNet, Inception, in different Inception modules, Inception Resnet versions, or ResNext versions, will give us that capability, because these guys followed these ideas, following the 5 years of, following the 5 years following the AlexNet. So I think that gives us a clear idea of how to design a convolutional neural network for extracting abstract features, not only for vision, for sound, and for other signal type data. Okay, these will be my slides. Any questions about ResNets and or other architectural designs, maybe relating to your projects? After this lecture, you may want to try different things in your projects if you haven't already. Any questions?
How is the accuracy calculated for this graph?
Let me check it, because I've taken this from another lecture's slides, this embedded deep learning. The accuracy is, this is a classification network. These are all classification networks. And the classification network accuracy is mean accuracy, mean hits. So it is like you have a number of categories. Which data set, you may ask? I don't remember. Yeah, exactly. A constant data set, which was not AlexNet, which was not ImageNet. I don't remember which data set. Let me check. So it's simply, they have a common data set. They have that. I'll check. I should check. I don't remember. But it's not an ImageNet. It was something harder, or a CocoNet maybe. Because in ImageNet, we have 90% accuracies, and even AlexNet has 50 something here, which means it's a difficult network. Yeah, yes, sure. I mean, if it's an edge operation, imagine it's a UAV. More operation means more power. Always less operations is. But there could be cases that you have enough power and you need accuracy at best. Then yeah, you could use. Then you could even use VGG then. As you can see, this is singularity. Well, actually, when they calculate it, they calculate the number of atomic operations like multiplication and addition. But convolution is all about multiplication and addition. So it is not number of convolutions, because it would have been not, I mean, clear in that case. Well, they somehow make this calculation when they are calculating G-flops for the number of operations they use. They make certain assumptions in embedded design. For example, if you are using a GPU, that means that multiplication operation takes a number of cycles. Addition operation usually takes a single cycle. So they assume such things. For example, addition takes 1 cycle, multiplication takes 5 cycles, and they calculate it. That's how they do it. Actually, when you're calculating the number of operations, the processor speed is also important. I mean, you could be doing the same calculations with higher speed, because 2 GHz processor is 2 times faster than a 1 gigahertz processor. It's doing the same operations. It's twice the time. Twice the operations in the same time. So what they do is they do some sort of flop calculations. Flip-flops is an element in logic design. Using flip-flops, you do logic operations, and using logic operations, you do additions. They kind of try to give how many G-flops you need to do the operation. These are beyond the scope of this course. I mean, to understand how an embedded device's computational complexity is assessed. It's a detailed subject, but that's what they do. Usually, when you're using GPU, they use this G-flop, indicating what kind of a GPU capacity you need to do it. Okay, your friend is asking questions about the x-axis. How do we calculate embedded deep learning? Yeah, I hope someday I'm going to start that course here as well, embedded deep learning. Okay, any other questions?